Good evening, children. Today we'll start a new topic, scalars and vectors. Or you can say vectors and scalars, doesn't really matter. Here I put a tagline, the facts of nature. I'll come back to that. But we divided this lesson, this unit into various lessons. One lesson we'll try to do in 1 hour, but it may extend to the next session as well. In lesson 1, we are only talking about the introduction. You can see that. Just what are vectors and scalars, how you represent a vector in terms of geometry and in terms of algebra, and what it means to say that two vectors are equal, and negative of a vector. If a vector is already there and a vector opposite to that, you can call the negative of this with equal magnitude if we have. And then unit vector, null vector, resultant of vectors. So some it's like initiating you into the process. So that part will be taken care. Then the most important thing, the addition of vectors, which keeps coming everywhere. Okay. What it means to say sum of two vectors, and two things. Actually, these 1, 2, 3, law of triangular vectors, law of polygonal vectors, and cosine rule are one and same in principle. Okay, here we'll give an algebra formula. Here we'll construct a parallelogram and tell how to find out the resultant or the sum of two vectors. Here we construct only a triangle and tell you how to get that sum of two vectors. But this cosine rule is applicable for this and as well for that. Okay, so that will be taken care in the second lesson. And then just based on that previous sum of two vectors, we'll do as many exercise and problems as possible. Exercise will be simple, problems will be slightly difficult. And then we have the lesson 4. Lesson 4, lesson 3, yeah. Lesson 3 is only exercise and problems, right? Now, lesson 4, there I do only some exercise and problems based on the mathematical formulation. But here we discuss elaborately the sum of two vectors in physics, especially the resultant motion. That is, say for example, when a boat is moving in a river, there is a velocity for the water. There's a velocity for the boat with respect to the water. So what is the velocity of the boat as you watch from outside? This kind of a river boat problems, for example, or aeroplane wind problems, for example. So that kind of serious discussion we'll be doing as the physics applications of sum of two vectors. Okay. And we would like to talk about difference of two vectors. Remember, apart from that first day's introduction, there is one most important thing, sum of two vectors. And then the second thing is difference of two vectors. Though we simply say difference is like sum only, like A plus of minus B, it is not so simple. It is one completely, when you apply to physics, it gives completely a different physical meaning to actually speaking. So we'll define the difference of two vectors and tell how you differentiate it from sum of two vectors. And even here we derive the cosine rule and examples in physics, especially the velocity relative, v of 1 relative to 2, velocity of a particle 1 with respect to particle 2 will be defined as v1 minus v2, and the special case of that relative velocity will be taken care. Okay, so here once again, here examples in physics we give, but maybe it won't be over in that one lesson, so we'll go for applications and exercise of difference of two vectors, relative velocity and relative acceleration thing. So in effect, we did two things, sum of two vectors and difference of two vectors until now. And then resolution of vectors into 2 and 3 dimensions. That is splitting of a vector. The effect of a vector is split into either 2 dimensions or 3 dimensions. And the purpose of it is basically, unlike that cosine rule, here we resolve 2 or 3 vectors into various parts and then use that resolution to find the sum or difference of two vectors once again. Okay. Yes, for every heading there is here applications and numerical practice and resolution of vectors will be included here, lesson 7 and 8 there. It can be over in one lesson or second lesson also you may take depending on your feedback. So now 3 are added, that is a plus b, a minus b, and then resolution. Right. After that, we have multiplication of vectors, which will be taken up in 9 and 10. One will go into the other. That's why I put the heading as lesson 9 and lesson 10. In this, there will be 3 types of multiplications. Multiplication of a vector by a scalar and multiplication of a vector by another vector in 2 ways, dot product and cross product. So after defining what it means to multiply one vector with another vector or one vector with a scalar, in this lesson we'll do only the scalar product, this one, and then a lot of practice and applications. Then multiplication of vectors, but the second one, what did I say? That A cross B thing will be discussed here. All right. So these are the main topics, children. If you summarize the whole lesson in a mathematical summary, if I give, apart from the introductory class where we define few things, if I give a mathematical summary, it is simple. Just vector A plus vector B. This is vector A minus vector B. Third, I'm not, of course, I'll write it here. For example, some vector A equals AX I cap plus AY J cap plus AZ K cap, like this kind of an expression, or resolving a vector into parts geometrically. If this is a vector like this shadow and this shadow will calculate. This is what you mean by resolution of vectors. So here I'll put a heading, in words, resolution. And then fourth one is A bar dot B bar. This is scalar product. Fifth one is A bar cross B bar. So these are the 5 headings, most important headings we'll be dealing with in this lesson called vectors. Okay, so that is what we're going to do in the next week. And as I told you, depending on the feedback, we can make it a little faster or slower or more elaborate. And lesson is going to be very dynamic and flexible. It all depends on your questioning. There's nothing like you need to sit quietly and then keep watching. Okay. All right. That's for the beginning. Now we'll start the lesson 1 there. Actually, I've sent you the write-up, isn't it so? Huh? So yes. Open it and tell me what is the first heading under lesson 1. What are vectors and scalars?
What are vectors and scalars?
Right. Actually, under the heading scalars and vectors, I gave a tagline, the facts of nature. What does it mean? Look, you may be a nature lover. You'll just go into the landscape and keep watching the trees, keep watching the movement of the leaves, and keep listening to the chirping of the birds, and you will meditate, whatever. You cannot say that you are studying nature there. Okay, it's completely a spiritual kind of an experience you are talking. But physicists study nature in mathematical terms. So in the very beginning, I would like to tell you people, nowadays there's so much information available on the internet. Okay, so you type a question, you get an answer. But everybody writes anything, anybody can write anything on the internet. So it's not that you should believe what all is told there. And when people write physics in popular terms, they actually talk it in a very loose way. So people think that's physics. It's not physics. Remember, physics has to be put in mathematical terms only so that it becomes science. Otherwise, your physics, my physics, somebody else's physics, there'll be too many physicses there. All right. It's a scientific method, basically. Newton was the first one to, what you call, start this. Though Galileo and Kepler also were talking in similar terms, it is the credit goes to Newton, where he thought naturally observed phenomena can be expressed in mathematical terms. So these vectors and scalars are the mathematical objects. Remember, if you say what it means to say, what it means to study physics in mathematical terms, if you talk, you need to frame laws of physics. Not even framing, there are physics laws already there, hidden in the nature. You need to discover those laws. And once you discover those laws, you have to express them in equation form, right? And tell me one equation which you know already that will consist either scalars or vectors in general. Though the physical quantities may be having different names, broadly speaking, they are scalars and vectors. Just can you recollect a formula and tell me Takshil in physics? You say formulas and equations, actually speaking, but remember, there are laws of physics. For example, if I write S equals ut plus half at square, this is law of freely falling bodies. And F equals ma, if I write, this is net force acting on a body. Okay, I'm putting bars on that because they are vectors. Just saying that force is push or pull is not enough. And if you say momentum before collision of two objects is equal to momentum after collision, this is another law called principle of conservation of linear momentum. Right? You might put that in words, but that's not important in physics. Ultimately, how do you show it in mathematical form? You just take any kind of a law like this. In that, you'll discover that you are either having a vector or another scalar. That's all. Here, displacement is a vector, velocity is a vector, acceleration is a vector, time is a scalar. So this force F is a vector, mass M is a scalar, acceleration A is a vector. Here once again M1, M2 are scalars, but U1, U2 and V1, V2 are vectors. That's why vectors and scalars are facts of nature. One way to tell that laws of physics are put in algebraic form. Another way to say that laws of physics are put in the equation form, which consists of vectors and scalars. That's where you mean to say, that's what you mean to say when you said vectors are facts of nature. Vectors and scalars are facts of nature. Okay. But I would like to remind you one thing. You know very well, scalars means a magnitude alone, no direction. Vectors means both magnitude and direction. But there is one more word here which I have to mention because I mentioned the words facts of nature here. They are tensors. At this level, 11th and 12th, we don't deal with tensors. That's why the lesson's heading is only vectors and scalars. If scalar has only one magnitude and no direction for it, or that scalar quantity is well defined, is well understood only by giving one number to it. That number is only the magnitude. But vectors are those things which require two numbers. One number is for magnitude, the other number is for direction. What do you mean by that? For example, mass we have. We'll say mass is 10 kilograms. That's all. So one number 10 is describing nature of this thing called mass, which actually characterizes the inertia of a body, basically, or which also characterizes its ability to produce gravitational force. Okay, but now when I said velocity, two numbers are required for me. Say, if a person is moving that way with 10 meters per second, this 10 is one number for the magnitude to tell how much speed, and this theta is, for example, some 45 degrees. So one number for magnitude, another number for direction. Okay, so this is a scalar. This velocity is a vector or vector quantity, you might say, scalar quantity, you might say. But most generalized form of these vectors and scalars is tensors. It has a magnitude, but multiple directions, you can say, to make it look simple. So scalars and vectors are special case of tensors. You understand? Because the word tensor is looking new, don't get scared, because tensors are there with us in the 11th and 12th class only. For example, moment of inertia, but we don't use the word tensor and we don't go to details of what is moment of inertia. We just manage it like scalar. Do you follow? So tensor is something which has the magnitude. That's for sure. Anything should have a number, amount, how much, but apparently it has got multiple directions. So the whole laws of physics which decide how the universe runs will be put in the equations forms, and these equations will consist of scalars, vectors, or tensors. That's why you will say the tensors are facts of nature, or vectors and scalars are the facts of nature. All right. And by the way, I've already talked about what is a scalar, what is a vector, what is a tensor. All right. Before I continued, your feedback. Come on. We'll write few. And one more thing, I wanted to just remind you people, because some new people have come in. I would like you to write running notes. This will be of two parts. One is what I ask you to write, what I write on the screen, okay, or what is there on the screen. Second thing is your own comments. Say, for example, here I did not tell you to write this, but you might write it. You should also, apart from writing what I'm asking you, should personalize your notes. And somewhere in the middle, I'll ask you to zoom your notes and show it to me. And the book should be a good book, a branded white pages notebook like Classmate or Papermate. Some names are there, no, I don't remember exactly, Navaneet or whatever. That kind of bound books I want you to keep, white pages, not rough books. Okay, not that coarse brown paper you buy, that's not correct. And write it neatly. This is more than a textbook. Anytime later when we solve problems, you need to keep that book by your side, and I'll keep reminding you about the formulas, the ideas we learned in the lessons. You keep looking at them and keep trying your problems. That's one thing right now. And anytime you get a doubt, you refer back to a particular lesson, to a particular idea, particular formula, particular problem you did. Many problems will solve in the classes. So that means immediate reference right now. I told you it's a textbook, almost like a textbook in which information from some various textbooks are there, right? I might have read so many textbooks by now, right? And synthesize the knowledge, so that the synthesized knowledge from many textbooks will come to you as one more textbook to you. That's the thing. And later you can also refer back to these notes in your engineering also, in the first year at least. or even when you go for interviews, they don't ask you serious things of engineering. They'll ask you some simple basics of physics and maths. So even there, it will be helping you. But for all this to happen, you need to have a permanent, nice, bound, white pages notebook and written properly. Do you all understand this? And as I told you, I'll be surprising you by asking you to show the notes you are writing. Okay. All right. We'll come back. So if you would like to have definitions, we'll give. Okay. Scalar quantity. Okay. Scalar quantity, I'll write first. Let us be done with that first and then come back to our vector. Here we are dealing with physical quantities, children. So a physical quantity which is best described by or defined by only its magnitude. What is magnitude? It answers the question how much. How much? You say 10, 5, 6. That's called magnitude. So for this kind of quantities, it requires just one number. How much you tell, that's enough. You already understood it completely. That's what I mean by best described by. And as I told you, you'll be writing and listening to me simultaneously. Yes. And it means it requires only one number to describe, right? It requires one number to describe it. And that one number relates to what? Tell me. That one number is only how much? The magnitude. All right. You can keep talking. I mean, like if you have a thing in the middle, just, you have that raising hand facility there, or you can just say, ask me to stop for a while and put your question. And I expect you not to put some funny pictures as you are whatever you call it on the Zoom thing. Because that will be distracting others. They'll be worrying as to what is this picture he put like that. Okay. So I told a physical quantity which is best described by only its magnitude. And what is magnitude? If somebody said, just ask the question, how much is that? So much. That so much is what you call the magnitude. And that means it requires just one number to describe it. And you've got examples of scalar quantity. Of course, remember this magnitude should not depend on the coordinate system. This magnitude will be independent of what? The coordinate system you put that in. Like mass is 12 grams, whether you represent it in XY coordinate system or some other coordinate system, it should be 10 kilograms only. In physics, the coordinate system is going to be very important. Try to understand. So I can add that statement that, yes, a physical quantity which has got only direction, you can say, which has got, you can say, whereas I told which is best described by. Okay. So, but this is much more, even in English wise, a correct way of stating it. Okay. So a magnitude which doesn't depend on the coordinate system in which you study it. So that's what you mean by scalar quantity. And then few examples, very well known examples. What? Tell me. Distance, speed, right? Even, okay, distance, speed, for example, work. These are famous things. I'll write first. These are all scalar quantities. You can give more examples later. Say, if you go to electricity, you'll talk of potential, electric potential, because this also work. a kind of work, a potential thing. Distance, speed, work, potential, mass are few examples of what? Scalar quantities. I told you already I want you to write. Now I know this, sir, I don't want to write no. Huh? And I'm going to check it. Be careful. And if I find you not heeding to my advice, not following my advice, not obeying my orders, you'll be taken to task. Be careful. So these are few scalar quantities. Can I change my screen, children?
1 minute, sir.
Wait a
Yeah. But meanwhile, if you have any question to ask, you're welcome. Vignesh, are you there in the meeting? In the session?
Yes, sir.
Okay.
Yes, sir.
Right. Manasa?
Yes, sir.
Okay. Gayatri?
Yes, sir.
Okay. Are you writing?
Yes, sir. Right.
Okay. And then, yes, Vignesh, tell me.
Sir,
Hmm.
sir, electric current comes under which, sir? Scalar or vector?
Scalar. I'm going to give you that because I did not put that in here because these are almost known to us. Distance, speed, work, potential, mass are popular quantities known as scalars. Huh? But there are certain
Yes,
quantities
sir.
like Vignesh is mentioning. When you look at it first, you think, that may be a vector, but it's not actually a vector. That's what I would like to show. Huh? So I would like to write one more statement for that. So this space is there. I'm going to use it here. Second statement, if I write, look, time. Sometimes people say time, I would like to make a vector. That's not vector. Time. Electric current. Huh? Time, electric current. Then what is that next one, which people misunderstand many times? Flux. Electric flux or magnetic flux. That is the number of lines. To put it in a loose way, electric field can be described by field lines. Similarly, magnetic field can be described by field lines. So flux is something which is somewhat like the number of lines passing through a particular cross section. So that is also a scalar quantity. Electric current is a scalar quantity. Okay, but how to know will be a problem actually. That though we'll give you few statements here for vectors, a few rules of check will give you, which you can keep applying. Mostly you will get it through experience as you keep dealing with the different lessons. There are special quantities like this, which look like some quantities look like scalars, they are vectors. Some quantities look like vectors, they are scalars. Here, time, electric current, flux are all more examples of scalar quantities. Right. I wanted to mention time, electric current, flux are all few more examples of scalar quantities. So you need to keep listening to me. If that's not looking clear, don't say sir is writing like that. That's only to help you to write there, not spoon feed you. All right. Now can I change my screen?
Yes, sir.
Right. Look. Vector. Look. Just the word vector, when you said, I'm not saying vector quantity. Actually, for us, there's no difference. Vector quantity and vector are one and same. Try to understand as far as physics is concerned. But there is, we do physics, we do maths, and maths we deal with vectors, and physics we deal with vectors. So I would like to, small differentiation I would like to bring to avoid confusion. Simply, a vector means a geometrical line segment, a directed line segment, a directed line segment. Okay, like this way, not this is a line segment, but put arrowhead like this. Okay. And of course, in mathematics, people write it in algebra form also. Even here we write in mathematical form. It is also mathematical, but it's geometrical. In algebraic form, I'll say. A vector people may write like this. Vector A equals sum 2i cap plus 3j cap plus 4k cap without mentioning which physical quantity is this representing. This actually people take it as a line only in mathematics. Do you follow? Mostly they'll take it as an ordered pair of 2, 3, 4 in the coordinate system there and join it to the origin. Most of the times they treat them as lines, that's all, directed lines. They don't bother whether that is a force vector or displacement vector or whatever. But here, vector quantity means a physical quantity which has both magnitude and direction. I'll go in your words only, which has both magnitude and direction and represented by a directed line segment is a vector quantity. Okay, and remember this direction and magnitude should not be depending on direction and magnitude are independent of what? Coordinate system in which the vector is placed. Coordinate system in which it is placed. And one more test will be, it follows, say, for example, the law of parallelogram of vectors. Or to make it general, it follows the laws of vectors. Or one which follows, it follows law of parallelogram of vectors. So this will be a complete definition of what a vector quantity means. To tell you, it doesn't depend on the coordinate system. I'll give you a simple example, but finish it off. I'll go to the next slide and talk about it.
Sir, what is the magnitude and direction and represented by?
A directed line segment.
Okay.
Which is represented by, you can write. And if you go for the notation, geometrically speaking, a line segment. This I'll put here notation. How do you write it? Geometrically speaking, just direct line segment only, nothing else. But in algebra, we'll write it capital A and arrow over it, or small a and bar over it, or simply bold face. If it is this can be done only in print. Do you follow? We cannot go on overwriting again and again like that. But when you look books, problem solving books, for example, Irido, he just only puts it in bold face. So should not think that it's a scalar quantity. So in algebra, we write either A this way, A that way, A this way. This is bold face. This is, people call it A bar. This is A arrow. Even that people call A bar, doesn't matter. So these are the three ways of representing a vector quantity, but the this includes both magnitude and direction. But the magnitude alone will be written as mod A or mod A, or simply light phase A. That means in future, if you write light phase A or B or P or Q, it is understood that you're writing only the magnitude of it. You're not showing it in the form of its direction. So this is for the notation. Okay. Tell me. I told you, you keep writing. Then I'll talk more on that. Actually, they should not depend on the coordinate system. When you say we are talking of a principle called principle of invariance, that means if the quantities keep changing as you change the coordinate systems, then they are not unique, and you cannot talk physics in terms of those what you call shape changing and color changing entities. They should be all the time same. Velocity means velocity. Whether you put here, put there, it should not matter basically. So scientists will try to find out those physical quantities which are invariant under many transformations. People say you can transform them into this and that, and but transform them means like you can move them linearly, you can rotate them, you can do many things, but the vector's nature should not change because there's a physical quantity. It cannot change. Okay. So what it means to us at 11th class level, I'll show you. Though that's actually the principle of invariance. What does it have for us? I'll show you in the next slide. And what is the coordinate system? Why it should not change? I'll give an example and show it there. Hope people are writing. Are you? Aren't you?
Yes, sir.
Right. Manasa, are you there?
Yes, sir.
Are you
Yes,
writing?
sir. Yes, sir. I completed writing.
Right. And Valli, Suraj, Jeevana Jyoti, Hari Prasad. Okay. Now, Children, can I go to the next slide?
Yes, sir.
Yes,
Going,
sir.
right. What it means to say that it should not depend on the coordinate system? I'll show you now. Say there is some force vector, for example, like this. This force vector, of course, remember, this arrowhead shows the direction. This length will be proportional to the magnitude. That means practical physical quantities there, when we are representing them on the paper, we should choose a scale. Like some block is there, for example, and that people say some rope is tied and some force of 100 newtons is developed here, we say. Now I want to show this 100 newton and this angle is 30 degrees. Say if you want to give our regular directions like east and west also, you can give this is east, for example. This is 30 degrees above the east, 30 degrees north of east, we can say. What can you say? This force developed in the string is 30 degrees north of east. So 100 newtons means, how would I show? I'll say I'll take a scale of 10 newtons equals 1 centimeter, for example. Then I'll draw a vector length of how much? 10 centimeters. Make an angle 30 degrees with this x-axis. Then whatever the physical thing which was there in the rope is converted to force vector here. And algebraically, I should write F bar. This is geometric representation. This is algebraic representation. And mod F equals, I should write 10. Do you follow? Hi, hello, children. Huh? Now, can I continue? This force of 100 newtons, this F bar, you can say 100 newtons is only the number, magnitude, try to understand, but actual length on the paper will be how much? 10 centimeters, right? Now, I would like to study in this coordinate system. I'll put some x, y like that. Okay. So there's a thing called resolution of vectors, the shadow. Like if I throw light from here, children, the shadow of this will be formed like this, isn't it? Do you follow? So this part is called the component of vector. What is it? The projection of vector, component of vector. So this is x component. That will be the shadow when you throw light from above like this. If I throw light from below, from here, the shadow will be formed here. So this 100 newtons can be written as a sum of these two vectors. What? Component vectors. But say if I take my coordinate system like this, somewhat rotate the coordinate system, for example, this way. Now the shadows will be different. Do you follow what I've shown here? Because that was too small here. So the shadow lengths will be different here and here, but the vector is still same. Have you followed my point, Aryan?
Yes, sir.
Here, okay, I'll change the red coordinate system slightly differently. Like this and this, for example. Now the shadow of this will be this one, isn't it? And this is the shadow on the y-axis. So some of these two will be once again this force. Some of these will also this force. So putting coordinate systems, we can get that force into those directions with different numerical values, but finally the original vector called force will remain same. So I can write here the components change when coordinate system change. Coordinate systems change, but not the, tell me, original vector. See, component vectors means what? their sum will give this vector. So I can represent my vector in terms of different component vectors depending on the coordinate system I take, but my vector will be vector. That's the meaning of it doesn't depend on the coordinate system, or it is invariant under rotation, people might say, rotation of the coordinate system. But that word you can keep aside for a while. Why, who were left? Let me see. Aryan, Abhinav, Enoch, Hariprasad, Sriram, Vignesh. I'm not able to catch. Dhanush Chandra. Say if you are due to internet, if you exit, you should enter again and ask for permission. You can put a message on the WhatsApp. 3 people are missing, 3 or 4, I don't know. Okay, so did I make this idea clear to you people that the vector should not depend on the coordinate system? Aryan, Vignesh?
Yes, sir.
Yes,
Huh?
sir.
So why? Remember, it's a physical quantity. Once you defined it, if you go on changing, it won't become physics actually. So they are real facts of nature. They are there. Me and you will be going after some time, but forces will be there all the time, right? So that's the meaning of the invariance of a vector under rotation for the coordinate system. Okay. Now, a few examples of vector quantities. Some examples. Most popular ones: displacement, velocity, momentum, linear momentum, we mean to say, right? And then force, okay,
Acceleration.
acceleration, right? Or some example. But certain quantities which are actually looking like scalars, they are vectors for various reasons. For example, area can be expressed as a vector. Similarly, infinitesimally small angles, d thetas, are angles generally are scalars, but d theta, infinitesimally small angle, are taken as vectors. Look, area, Vignesh, I'm answering it. Huh? Look at this. If you have already learned something, I'll show you that. Look, if I take a rectangle, for example, of this is 4 centimeters, this is some 6 centimeters. If you say, you'll simply say the area is 24 centimeters square. Where is it? Why? That is taken as a vector. It's all right here. You can just say it's a scalar, but in physics, there's a problem. Look, this will be one vector. If I represent this by another one vector A bar, this by B bar, their product will be a vector like this. This is A, this will be a vector like this. This is B, this is C. People say C, vector C equals vector A cross B, we say. C will be towards you. And finally, you will find that this magnitude of C will be simply equal to this area. You know, magnitude of this area, and this area will be the magnitude of this vector C, which will show anyway in cross product. I'll show you later. So area can be made a vector area, actual area will be in the plane, but area as a vector is perpendicular to that plane. So that is one thing you need to take. And also this, if I rotate through some 120 degrees, all that 120, I won't give it as a vector, but d theta, small rotations, say for example, this is anti-clockwise rotation. This d theta will be taken as a vector in the right hand thumb direction. What is right hand thumb direction? You turn the 4 fingers of your right hand in this direction. You can stretch them along that positive x-axis. 4 fingers, you stretch like this and think of turning them towards the angle. The way the thumb shows is the direction of d theta. So if I do that, my thumb comes out like this. It comes out like this. So d theta will be taken as a vector in this direction. So two things, area and d theta are vectors I wanted to tell you. Children, please write it and remember it slowly. Things become even more clearer because we're going to use them as vectors in future. If this book is there, area of this will be like this, for example, or like this. Which way we'll see. But the actual area here, you can see this, no, will be made into a vector like this for our own purpose. This area of the book here, which is coming as a length into breadth, some number will come, no? So that will be represented as a vector with that magnitude as its magnitude, but the direction being perpendicular to the plane of this area, which will be using many times in our physics. Children?
Sir, please explain that example once.
Angle. No, your voice is all the time breaking. The internet, I think, is an issue with you. Can you tell me what are you talking? This d theta thing?
Please explain the example once.
Which example? Area?
Yes, sir.
Look, we'll anyway in the cross product will go there. If you know it, I can talk more, but otherwise, what? Just take this. This book is there, right? Book's length is something, breadth is something. Area will be length into breadth, you will say. So the over that is. But this area of the book can be represented as a product of, as a cross product of a vector along length and a vector along breadth. This breadth will be taken as one vector. Length will be taken as another vector. Their product, when you do, it gives you area. Try to understand. But with a particular direction like this. So area is here only, but area vector is like this. First, get this, the information you get first. Suhita, area, which has got some number, is made into a vector like this, into a direct line segment like this. So if area is 100 centimeters square, if the area forming, if the rectangle forming formed by these two sides is in this plane, the area related to that vector will be this way, for example. So 100 centimeters square is the magnitude, and area as a vector is perpendicular to the plane of this rectangle. It has a purpose. Don't worry. Yeah, Abhinav, tell me.
Sir, is volume a vector too?
No. Volume is not a vector. Yes. Huh? That also I will show that later. That will be represented as a dot product, not as cross product. Okay. Children. And this will be used so much. Even in intermediate will also we use all this area as a vector. So Suhita. So first lesson, of course, we've got few more examples. It's not over yet. But remember, though I've given you the headings like that, the headings may not be finished on a particular day. So they'll go into the second lesson. So you need not bother about it. Look, the first one we talked was, so how many headings I have? This is over. This is over. We're only representing notation of vector. Notation of vector is over. This thing we did not commit, but this all will become very fast. Okay. Now I'll continue. I'll be giving many examples. So though the headings look small, they take a lot of time. We are still giving the examples of vectors and their how to represent them. If I made area a vector, that vector area will be perpendicular to the plane of the area. That's what I want you to catch first. And d theta will be a vector in the right hand thumb when the angle is rotated in the anti-clockwise sense. So do you follow this point? If it is measured like this, d theta will be a vector towards C. So that d theta. Hello, children. Are you there?
Sir. Yes, sir.
Yes, sir.
Something happened. Why? What share has gone or what?
Your voice was breaking, sir.
Acha, I think the internet is unstable. Okay. So we are somewhere here. Yeah. So only part of it went, I think. The speed has come down, I believe. Okay, then. This is not yet over. Will be tomorrow's lesson will still consider as lesson 2, but finish the remaining headings in that lesson 2 tomorrow. Okay. So I'll upload the video again. Just you can watch it once again if for clarity. And then we'll continue because I think the internet is unstable only. Just one more minute I have. So we'll close it for now. We'll come back tomorrow. Thank you.
Thank you.
Thank you, sir. Bye.
Thank you, sir.
Huh?
Yes, sir. Bye, sir.
Hello?
Thank you, sir. Bye, sir.
Vignesh, are you asking a question?
No, sir.
No. Okay. Somebody else was saying something. Vishnuvardhan, are you saying something? I'm ending the meeting, children. Probably I think that's not going through properly.